Hello and welcome to my ECEE421 Final Project. This project will discuss the NE5234 Operational Amplifier Design. First, I would like to take a look at some of the PSpice design parameters that were used to model the transistors. The saturation current was mainly used to control the emitter area. Both of these, for both the PNP and the NPN, this was set constant at 14.34 femtoamps. This was done for simplicity and so that transistor would be a good match. The early voltage determines the output resistance of the transistor. A higher early voltage is better because I would like to have more of a loading effect when it comes to current mirrors. Ideal current mirrors will have much larger output resistance, and also early voltage can help impact the gain, the overall gain of the amplifier circuits. For the PMP, this factor was chosen to be 115.7 volts, and the NPN was chosen to be 74.03 volts. The DC current gain of the transistors would determine how much the difference between the current into the base would be from the current into the collector. So a smaller base current would yield to a larger collector current with a larger beta. This would also impact the gain of the circuit. For the PNP, a DC current gain of 231.7 was used, and for the NPN, a current gain of 416.4 was used. These models were based off of the 2N3906 and the 2N2907 PSpice models. First, I would like to take a look at the biasing circuit for the Op Amp. Q49 and Q60 here form what is known as a Widlar current mirror. This, on the right here, this circuit is a simplified version of the larger circuit. This simplified version was used to tweak parameter values of the transistor such that a 6 microamp bias current was achieved at the collector of Q47. This current would be used to bias a lot of the transistors throughout the circuit in the Op Amp. Q60 had needed an emitter area that was twice as large as Q49. To achieve this, the saturation current was simply multiplied by 2. The bias point from the bias stage comes in and is connected to the bases of Q11, Q12, Q13, and Q14. This is used to apply a 6 microamp bias at nodes 1 and 2, which biases the differential amplifier at the inverting and non-inverting inputs, at least the NPN side of the inverting and non-inverting inputs. These inputs are also coupled to two PNP transistors, which are biased at bias points 3 and 4. It was found that most of the gain was achieved in this input stage, and The outputs are found here at node 9 and node 10. The inputs from the first stage to the second stage are here at node 9 and here at node 10. Transistors 15, 16, 17, 18, 19, and 20 are mainly for biasing. The input from the bias stage, bias 1, is applied to the bases of each of these transistors to achieve the various currents that are needed throughout the second stage. Q29 and Q30 form a Wiley current mirror, which is used for further biasing. But mainly, the interesting part of this stage is Q21 and 22. These emitter followers reduce the loading effect on the first stage, which increases the gain of this first stage. The main gain stage of the second stage is formed by these differential pairs, which is output to the output stage through nodes 25 and 26. Here's a look at the output biasing circuit. Again, this is mainly just for biasing. Not too much interesting going on here. And here's a look at the output stage. Node 25 from the second stage comes into here, and 26 comes into here. The main purpose of the output stage is the current gain, which is achieved in Q74 and Q75. On the left, we have the expected values for this circuit taken from the textbook. Again, this textbook can be found in the references section. And on the right are the simulated circuit currents. Main differences found here are in currents 1 through 7. Current 1 and 2 should have been 0, but there's about 2 microamps there. That was unexpected. Q3 and 4 were biased a bit lower than expected. Transistors 12 through 14 were also a bit lower than expected. Transistors 37 and 38 were a bit lower than expected, while transistors 40 through 43 were a bit higher. Two more that were a bit higher than expected were 46 and 56. 56 was about twice or 3 times as what it should have been. 64 was a bit smaller, while 65 was a bit larger. 64 was a bit larger and 65 was a bit smaller. 66 was also a bit smaller, as well as 71 and 74 and 75. These differences could be due to differences in design, specifically DC current gain and saturation current. Now I would like to take a look at some of the measurements that were taken to verify the functionality of the transistor based on the op amp, based on the given datasheet for the NE5234. Using this configuration, I was able to measure offset voltage by grounding both the inputs and applying a feedback resistor, which would result in a gain of 1000. The voltage at the output was read and divided by this gain of 1000 to find the input offset current. The common mode rejection ratio was measured using this configuration. This was calculated as the input voltage measured here divided by the output voltage measured at the output multiplied by the gain here, which was about 1000 plus 1 because of the non-inverting input effect. The common mode rejection ratio was then converted to decibels. So here's a look at the datasheet compared to the simulated characteristics in the bottom right here. The total supply current of 1.282 milliamps was lower than the supply current found on the datasheet. The input offset voltage found here and here was also a bit lower for the simulation. The input offset current was basically 0, which was different from the datasheet, which was at about 3 nanoamps. The input bias current, which is the current that enters through the inverting and non-inverting inputs, was about 12.97 nanoamps. Ideally, this would be 0. As for the datasheet input bias current, this is typically about minus 90 nanoamps. The common mode rejection ratio was measured at 87.811 dB. From the datasheet, this was closer to the minimum value for the NE5234. The open loop gain was found to be about 90.5 dB using a 5-volt supply voltage. This was around the minimum and typical of the NE5234. The voltage swing was measured with both an RL of 2K ohms and 600 ohms. This fell within the range of what the datasheet would expect. Overall, the DC performance of the simulated circuit was just as good, if not better, than the performance found of real devices on the datasheet. This is expected, although, because of the use of more ideal components in the simulation. Here's a look at the stage-by-stage breakdown of the gain as well as frequency response of each stage. At the input stage, most of the gain was found at max about 70 decibels. The 3 dB point was found at about 20 hertz. As for the second stage, the 3 dB point was found at about 200 kilohertz. The maximum gain, however, was only about 15 dB, although the emitter followers could have had an impact on the gain on the first stage, which is why it was so large. Adding these two gains together, as they were found in dB, resulted in about 85 dB of gain. And here's a look at the output stage. This stage had slightly more gain than the second stage, and in total there was about 100 dB of gain, although this is different from what was found with the 5-volt supply. This is because a 5.5-volt supply was used in these measurements. The 3 dB point was found at around 900 kilohertz here. So the lowest 3 dB point was at about 20 hertz in the input stage. Here's a look at the overall frequency response of the simulated device. The 3 dB point was found at about 100 dB at a frequency of 20 hertz. The maximum gain was the addition of the gain throughout the 3 stages in dB, and it was about 102. This was all done with a 5.5 volt supply. Here's a look at the application of this op amp as an inverting amplifier with a gain of 10. The feedback resistor and the input resistor were connected as such, and therefore the gain would be the feedback over the input, or about 10. The circuit was configured like this for the non-inverting amplifier, and for the inverting amplifier, and the non-inverting input was grounded. The graphs on the right show the application as the inverting amplifier, the input signal in blue, or 10 times the input, and the output signal in orange. As you can see, they are about the same in amplitude, meaning the output was about 10 times the input as expected, and it was inverted. The graph below that shows the gain versus frequency in dB, in the gain in dB versus frequency for a inverting amplifier of unity gain, meaning the feedback resistance was the same as the input resistance. The 3 dB point here was found at about 2 megahertz. And of course the gain in decibels was 0 because it was done at the 3 dB point. Was done with a unity gain. Now I would like to compare the simulated model with the PSpice LM3224 model. This is also an NE5234 Op Amp and should yield similar results. This was first seen in the measurement of gain versus frequency, the open loop gain. The maximum gain was about 100, and it started to drop off. We hit the 3 dB point at about 10 hertz this time. This led to a gain bandwidth product that was much less than was found before. This was about 1 megahertz gain bandwidth product, whereas before in the simulated version that I created, it had a gain bandwidth product of about 2 megahertz. Also compared in the bottom left was the output voltage swing. Oddly, the max output voltage swing did not reach the positive supply. Overall, the performance of the model that was simulated with transistors performed better in both these regards. As for the performance as an inverting amplifier, the gain of 10 was seen by both, although the frequency response in the actual op amp or the simulated op amp was a bit lower than the one model in PSpice. Here's what a similar amplifier might look like made out of MOSFETs. The MOSFETs have different characteristics, and thus the performance of this amplifier would be different. Specifically, the frequency response would have a lower cutoff frequency because of the capacitance at the gate. Also, this amplifier would have a lower gain because of the lower transconductance of the MOSFETs. And finally, this amplifier would have lower power consumption because there would be no current entering the gate of each of the FETs, and there would be less devices here. Here are the sources that were used in creation of this project. Here is the textbook that was referenced earlier, specifically section 6.8 was used, and a lot of chapter 6. And here is the source that was used to find the common mode rejection ratio and the biasing circuit for that. I hope that you enjoyed this presentation. Thank you very much for your time.